Hello, hello. Hello, there we go. So, sorry about that. All right, Science 30s. I want to just take a minute on transformers just to finish up this last section. There's an excellent video on Michael Faraday's induction ring. It's actually the history behind the transformer. Um, the idea was that he took insulated wire in blue here and he wrapped that around an iron core, and he was hoping to generate current in this case, the red loop, the red coils of wire. And what he learned is that um, putting current through the blue cable actually caused a magnetic field to be created in the iron core. Excuse me, and that magnetic field actually caused current to flow in the red coil. And how that works actually, yes, and there's the number of turns on it matters, and we'll see that right away. What I wanted to show you quick though was a of how it basically works. So here, maybe I'll just do this here. So let me start over here. This is basically what a transformer looks like. What a transformer does is it takes voltage coming in from one direction and it converts it or changes it to a higher or lower voltage. And it uses a device that looks something like this, which you may have seen at some power stations. Excuse me. It's got those vanes on the side that actually help with cooling, and inside it uses PCBs, um, which are that's an organ from our organic chemistry unit. It's an oil that's used to actually keep the coils cool. So this is just a quick review. If you move a magnetic field, see the north and south pole, if you have a changing magnetic field, what that causes is an alternating current in blue. So you see this loop of wire. The blue arrow is showing the change in direction for the current. So if we make a loop of this wire that has alternating current, the wire on the right actually just shows what, reminding you, if you move current through a wire, it generates its own magnetic field. There's a magnetic field created around it. So if you make a loop of wire and that current is changing direction, right? Note the blue arrows are going back and forth. If that's happening, then you're creating a changing magnetic field. It's as if you have a bar magnet and you're flipping it. So like the north and south pole are changing. Now, actually, here let me pause that for a second. So the question was, could we get current to flow in a separate loop of wire? You see this over here on the right. If we have current flowing in the wire on the left, could we get current to get flowing in the wire on the right, even though we're not connected to it? Like, could we get electricity to start flowing in that? So what Faraday realized is if you connect these two with an iron ring, okay, now iron is magnetic, so it can become magnetic or act like a magnet. And you can see here, just right now, it shows these red arrows. It shows that there's a magnetic field in that's changing direction in the iron ring. Okay. And if that's happening, then that's going to cause current to flow in the second coil, which is that's the genius behind transformers. Now, the E here in this one is actually voltage. We'll see that comparison in a second. But you can see here there's greater number of turns on the right. The N, or the secondary coil, that's what NS. N is the number of turns. S is the secondary coil. So there's a greater number of turns. But I'm just pausing the animation here. The changing magnetic field is the same on both of these coils of wire, but every individual coil will experience this changing magnetic field. And so, in a sense, each coil, or if you have more coils, you're going to be moving more current. Okay, you'll be moving more electrons in that coil than in the other one. So here the capital E is represented as voltage. The subscripts are S and P. P stands for primary, as in the primary coil. S stands for secondary. So anyway, let's let this animation run. It's exactly how we control electricity. And we can scale it up and scale it down as often as we need. So again, there we go. We have the voltage, or E. I think E is really standing for electrical energy. You have primary and secondary. So just I'll show you these formulas here shortly because we have a great compression of them. But look, you can see here in the animation, we can easily change the number of coils on one side. And the first one, so yeah, look at that. We can go back and forth. I should back it up here. When we're looking at this one, this would be a step down transformer. And you'll see that with the math. It would mean we'd have a primary voltage would be high, and then the secondary voltage would be low, because we've gone from high to low and the number of turns matches that. So we go from a high number of turns to a low number of turns. And then here, just let the animation run, it'll flip. We can easily do the reverse. So we can put more coils on the second coil, on the secondary coil, I should start using that word correctly. And the primary coil has fewer coils. So this would be a step up transformer, because the voltage would be going from a low voltage to a high voltage. And anyway, the actual transformers get a lot more complicated than this, but this is the basis and the simple understanding for a transformer. You can see here, this is a three-phase transformer. There's actually three coils lined up together, and that actually lines up with what this guy really is. Okay, so there's, I don't know, you can see that there's three inputs and three outputs. The inputs are, depending on which one's in and out, you could go from high to low or low to high, it doesn't matter. So having showed you that, I now want to show you the just the ratios for it. The math isn't too bad because it's always ratios, but you need to be comfortable with that, and it is in your data booklet. So again, here's the simple comparison. So what we look at here in a transformer is the primary and the secondary coils. You can see them right here. And in this one, to start with, well, we have the same number of loops on both sides, so the voltage doesn't change. It's 8 volts. It's 8 volts over here, and it's 8 volts over here. 4 turns, 4 turns. Primary, secondary. Okay, not too surprising there. If we change that, though, we went up here, this would be a step-up transformer. I'm hoping you could see really quickly that you could identify it as a step-up transformer, primarily because look at the secondary coil. It's got there's way more turns in the secondary coil than in the first one. So this would be a step up. And just look at the ratios here. It's really, I think it's pretty easy to follow. If the number of turns doubles, so if you went from 4 to 8, then the voltage would also double. It would go from 8 to 16. So that's a nice, straightforward ratio, and I don't think you'll have too much difficulty identifying that. Let's look at the opposite, a step down transformer. In this case, the incoming or the primary voltage is 8 and the number of turns is 4 as before, but now we have stepped it down. Okay, we went from 4 turns in the primary to 2 turns or 2 loops of wire in the secondary. So this is definitely a step down transformer, and we could easily determine the voltage, in the second coil if we didn't know it. Okay, now, so what that leads to then is this expression right here: the number of loops on the primary coil over the number of loops on the secondary coil. So that ratio will exactly match the ratio of voltage. Okay, so actually in your data booklet, it has this formula for ideal transformers. Now they say ideal because there is some power that's lost. It's not 100% efficient, but under ideal conditions, you won't be losing any energy from the first coil to the second coil. And so then this expression holds. But there's the first one, that's the number of turns, N, in the primary is equal to the number of turns in the secondary, which will equal the voltage in the primary over the voltage in the secondary. Okay. Now, the second principle behind transformers is this, and this is really helpful a lot of times. The power in to the primary has to equal the power out in the secondary. Sometimes I like to write it like this: the power in is equal to the power out. Okay, I mean, well, however you want to remember it. But the important thing, though, is that power is equal to voltage times current. Okay, and that's exactly what this looks to establish here. So the voltage in the primary coil and the current times the current in the primary coil has to equal the voltage in the secondary coil times the current in the secondary coil. Okay, maybe just clear that off. So you can kind of see that written up here. I just wrote it once so you could follow it. So there it is right there, and they took the liberty of rearranging that. So instead of VI equals VI, they put all the V's on one side and all the I's on the other, and then it looks like this. Okay, so the voltage primary divided by the voltage secondary will equal the current secondary over the current primary. So the only thing you have to remember here is the in this first expression, primary and secondary are in the same position, like the numerator and denominator. If you see how that works. The others are flipped, so just be careful you don't write them too fast. I think you could get them. You could keep thinking that it's supposed to be, the primaries are both in the top. Well, they're not for these second two expressions. Okay, so we can identify the current in the secondary and the primary coils using this middle formula. Okay, so if we just have the number of turns in the primary and secondary coils, then you can find the current in the secondary, the current in the primary. What you may use more though is this last one here. So if you know the voltage, the voltages in both, and you know the current in one, you could find the current in the other, or vice versa. Okay, but again, these the P and the S, or the primary and secondary, are flipped when you compare the voltage in the first part of the formula to the current in the second. All right, so oh yeah, that was just the key. So I want to just work out a couple of problems with you here. I'll just show you them. So here we got a large neon sign. The power supply takes a 240 volt input and then uses a transformer to increase the voltage to 12,000, okay, to operate the sign. So based on that, if you know you're going from 240 to 12,000, that sounds like an increase or an up, okay, and that's exactly what it is. This is a step up transformer, okay, and then it says if the transformer has 125 turns of wire on the primary coil, okay, so let's just identify what that would be. That would be the number of turns on the primary, NP. Then what's the number of coils on the secondary? So it wants to get NS, okay? And here it is here. It says, we have the two voltages and we have the primary number of turns, but we don't have the secondary. So you just set up this simple ratio. Sorry, it's a bit blurry there. Maybe we shouldn't blow that up too much. And you solve for the number in the secondary coil. And yeah, it's going to be a lot bigger for sure. Because we're stepping it up here. So we need more coils in the second coil, as we've been kind of just learning about transformers. So, and then the last one, it says, if the power supply requires 25 amps of input current, how much output current would there be powering the sign? So there's 25 amps of current coming in to this transformer. How much current is coming out in the secondary coil? Okay, so again, we're going to come up here, and it looks like if we're dealing with voltage, because we know the voltages, right? We knew the initial and final voltage, and if we know the initial current, we are definitely going to use this guy again right here. Okay, and that's what they show here. So we've got the incoming voltage and the outgoing voltage. So the incoming current would be IP. Now, as you're careful here, that goes here. So anyway, I don't want you to stress about memorizing these relationships. Just lean on your data booklet, okay? And be very careful that you don't flip them. You don't put them in the wrong position. But, that means we know these three, and effectively we're trying to solve for the current in the secondary. And I mean, if you're following the ratios, right, it's really VI is equal to VI. And so if the voltage goes up significantly, then the current has to go down, okay, proportionally, right? Because these two have to equal each other. Anyway, this maybe isn't that surprising, but obviously the math may not be obvious until you do it, but there it is right there. And the current is 0.5 amps. So it is definitely dropped down significantly. But that's to compensate for the boosted voltage. Like we need electrons with way more energy per unit of charge to run this silly sign. And so that's why we use the transformer. And lots of devices do that, lots and lots of them. Okay, so let's just end on this one. I like this picture too because it shows you all the steps, okay? So we grab the coal from here, take it to the coal-fired generating station. We do that whole process that you learned about earlier, and you produce a voltage. And that voltage gets stepped up. So there'd be step up happening here. Okay, and these monster lines, again, the biggest ones I've ever seen are 500 kilovolts. Okay, so the voltage in these high voltage transmission lines is really, really high. And then it would come to a substation, and there's the transformers that we just looked at. They're right there. So this would take that voltage and it would likely step it down. Now, it wouldn't step it down to, 240 volts or anything, because that's not going to transmit very well through the power lines. We still have a ways to go to get to people's houses. So this might step down to, I don't know, it could be anything. Maybe it's like 270 kilovolts, or I don't know, maybe it's like 130. I don't know. Like the numbers vary depending on distance and range, and I'm really not sure which ones would be a standard. But anyway, for sure it's not down to 240. That doesn't happen until so that substation, then the electricity makes its way here, then it happens right there. These are the ones that take whatever this voltage is and they step it down to 240. Okay, that's a standard. Now, obviously, if you need more than that, then you'd have a different transformer. But a standard transformer, the ones that you see, outside your house, up in the lines, if you have overhead power lines, you can see those transformers. So they'll step that down to 240, which is what comes in your house, and then all of the standard plugins have half of that, 120 volts. Basically, there's two 120 volt lines, right? That you wire them in parallel, they make 120. You put them in series, and you can make 240, which is what your oven and your washer use. So let's just end on these here. It says the transformer in a power pole takes an input voltage of 4 kilovolts. Okay, now what you have to be really careful here is there's a kilovolt there, and we're comparing that to 240. So really that's 4,000 volts. Okay, 4,000 volts to 240. Well, that sounds like a decrease to me, so that should be a step down. Okay, that's definitely a step down transformer. And it says there's 180 turns of wire on the secondary coil. So that is NS. Okay, the secondary coil. All right. And then it says how many turns would there be on the primary coil if we're going to make this change. So because we know the voltages, we're going to use the first expression here. So what that means is the voltage in the primary is 4,000, and we're going to divide that by 240 in the secondary. Sorry, I'm writing over this. I'll erase it after. But that's going to equal a number of turns in the primary coil, which we don't know. Sorry, this is it's primary over secondary, right? And then voltage in the secondary is 240. Oh, sorry, wait, I already said that. The number of turns, sorry, in the secondary is 180. Okay. So again, we set up that ratio, and I guess I'll just mention this answer here and I'll leave it up. Because yeah, that if I did my calculations right, that should come out to 3,000. Okay, turns. So that's NP, the primary. So it'd be 3,000 turns. Okay, so you'd have a high number of turns down to a low number of turns, and that should make sense for a step-down transformer. Okay, let me just make a little room here. Let's go to the next question. It says the current supplied to the home is 100 amps. What would the current be to the transformer? Okay, so what we have to be careful here is the current supplied to the home. Is that the primary? Would that be in the primary or the secondary? And if it's supplying it to the home, that should be the current. That's the secondary current. Okay, it's not the current that we started with. So you kind of have to follow the current basically. So then what we're looking at here is the voltage in the primary over the voltage in the secondary is going to equal the current in the secondary over the current in the primary, like that. Okay, and we still have the voltages, right? 4,000 and 240. So that would look something like this. Okay, we'd say 4,000 volts over 240 volts. And we don't know the current. Oh no, we do know the current in the secondary. We want 100 amps to be coming into the house. And so we just cross multiply and divide there, okay? So the current coming in should be 6, okay? And that makes sense. We want the current to be as low as possible in the transmission wires so that we're not losing energy due to heat or anything like that. And then, yeah, once we're really close to the source, that's when we can crank up the amps because we need them, okay? Obviously, we'd have to control those amps as you go into your house, which that's what the circuit breaker is for and all the devices and everything else. But so let's look at the last one then. So I guess I could just leave the answer here. This is 6 amps. So now the question backs up. At the coal-fired generating station, the station's transformer is provided with 20 kilovolts. Okay, the transformer then boosts this voltage value to 230 kilovolts for transmission. Okay, so this is the voltage primary, and this would be the voltage secondary. Okay, because we're going from 220 to 230 kilovolts. Now they're the same unit, so that's fine. I think you guys can see easy enough. That's a step up. Okay, we're definitely increasing the voltage, going from the power station to the transmission line. Now, part B, most customers only require 240 and 120. Yeah, that's the standard. We talked about that already. So why does the company boost the 20 kilovolt all the way to 230 kilovolt? Well, I'm hoping now that we've talked about that enough that you're starting to realize that the benefit lies in this expression. If you don't reduce the current, sorry, let me move that up. If you don't reduce the current, then the power lost. We could do a power lost calculation, okay? P lost. If that current is high, whatever the resistance is, you're going to be losing more power due to heat. Okay, you'd be losing electrical energy due to heat. So we want the current to be as low as possible. And to do that, you have to increase the voltage, okay? So, we're looking at power in is equal to power out. So, VI is equal to VI. And if the initial voltage in this case is 20 kilovolts, okay, and then we step that up to 240, okay, then correspondingly, what will happen is we want to lower the current. So make that current as low as possible. All right. So let's see. So part C there, if we transmit, if the power transmitted is 1.2 megawatts, what's the current in the cables? Okay. So in this case, if you know the power already, okay, and in the cables, we know what the voltage is. It's 230 kilovolts. Okay, so power is equal to current times voltage. And if it wants the current, current would equal the power divided by the voltage. And the power, again, it's 1.2 megavolts. So, or megawatts, sorry. So that's 1.2 times 10 to the 6th watts. In order to do this math correctly, we're going to have to break up these units. Same with the voltage, because, oh yeah, this is how much current oh no, sorry, I'm looking at C. Yeah, so we need the voltage in the cable. So that's going to be 230 kilovolts. Or really that's 230 times 10 to the 3rd volts, okay? So, sorry, so you can read that. Yeah, the point is we're going to need to put those in the correct units, but doing that will let us solve for the current. Now, this is a rounded value. When I first did this, the math wasn't exact, but I realized we're a little limited by significant digits here in terms of expressing our answer, because there really is a big decimal after that. But for now, let's just leave that. The current looks like it's about 5.2 amps in the power cable, which is low. That makes sense. Now in D here, it says how much current is the generator supplying to the transformer at the generating station. So this would, if now we're looking at not the secondary voltage and secondary current, but the primary voltage and primary current. Okay, so if we use the expression here, it would be the voltage primary over the voltage secondary would equal the current secondary over the current primary. All right, and for this one, the current was 20 kilovolts. By the way, we can just leave these in kilovolts. That's not going to hurt anybody because they're the same unit, so they'll just cancel out. Okay. The secondary current, we figured that out. It was 5.2 amps. And then the primary current is what we don't know. Okay. So again, cross multiplying and divide. This actually comes out, if we round it, I think I got 59.8 amps. Okay. So I guess if we are sticking to two significant digits, this will round up to 60 amps. And actually that, because in part E it says, can you calculate your answer using a different equation? Yes, you can. Because what we can say is the power in, or the power primary, has to equal the power secondary. Okay. The power in has to equal the power out. So, because the power, or the power is 1.2 megawatts. Okay, sorry, megawatts, and that has to equal the oh wait, sorry. Actually, the power the power in, I guess I should back up. I'm doing that backwards. The power in should be the current times the 20 kilovolts. Okay, so it's like VI is equal to VI. Okay, actually, let me do that so that it matches what we're using on our formula sheet here. So oh yes, so that means that we have 20 kilovolts times the current primary, which we don't know, but we already have the power output. Like I did get the voltage and the current, but it did tell us what it was. It was 1.2 megawatts, or 1.2 times 10 to the 6th. Okay, so setting it up like that, I can now solve for the current primary. And doing that, I actually get, this is 100, that's kilovolts, and this is 120, or sorry, 1.2 times 10 to the 6th. So 1.2 times 10 to the 6th divided by 20 times 10 to the 3rd. Okay, that gives me a current of 60. Woohoo, 60 amps. So lo and behold, I found I can do the same analysis using the same, or coming up with a different way. So anyway, that's a quick overview on transformers. What I'm going to post shortly are just some practice questions for this entire chapter, and I'm probably just going to call it like a homework test for you to work through, and I'll provide some answers, because we've basically finished with the first chapter in the physics section, and we're going to move ahead to the second one in probably another day or two. So keep up the good work, you guys.